Hello, so my name's Joe. I'm the team lead of 5 students. We are currently studying an FDSC in Marine Technologies and an FDSC in Manufacturing and Mechatronics.
My name's Kit.
And my name's Ollie, and we're part of the design team.
My name's Andrew.
And my name's Glenn.
And we're the programming team.
Welcome to Team Project 15. We are from the University Centre South Devon, based in Paynton. My name is Matthew Prowse. I am the project lead and lecturer on the FDSC Marine Technologies. Also to acknowledge Joseph Ross, who also works at the college and has supported this project throughout this year. I'm going to introduce you to the students. They are Joseph Oram, Kit Monaghan, Oliver Hare, plus Andrew Hurst. They've been working really hard this year on Project 15 and the Marine Autonomy Challenge, and hopefully they're going to demonstrate that in this presentation. So leading nicely on, I'll pass you over to Joseph Oram, who's going to talk to you guys about the background and introduction.
Hello. Today we're just going to briefly talk about these things on the slide here. We're going to discuss the design of a marine autonomous surface ship, also known as MASS, which will hopefully identify and remove plastic from the ocean. So we're going to begin with identifying the background, the problem that is plastic in the ocean. And then we will move on to the design process and solutions that we have come across certain problems during that process. And then we will talk about programming and solutions again to programming problems that we have come across. Next, though, I'm going to discuss about the background content. So the waste impact upon the environment is absolutely devastating, especially plastic waste in the ocean. In 2010, 192 coastal countries generated 275 million tonnes of plastic waste. This plastic is ingested by all sorts of marine life. Veterinary records themselves stated that over 100 species of birds, of marine birds, are an example of plastics and waste being ingested by marine life. The financial cost is also high. The government released the figure for keeping the UK streets clean in 2016 to 17 at almost £30 per household. We believe that MASS can be a solution for reducing financial cost and environmental impacts. Next, I'm going to hand you over to Kit to talk about the design brief and specifications.
Hello, my name's Kit, and today I'm going to be talking about the design brief and specification for our team's project and our vessel. And we've had to consider the 3 challenges that the MAC Challenge have given to us, which are navigation, colour identification and speed. So the vessel design will have to be programmed to navigate through an obstacle course composed of different coloured objects and be capable of operating at high speeds to be able to surpass rival groups' vessels without collision. We will need to take into consideration the weight of the vessel to obtain a suitable speed and stability to help navigate the course efficiently. In addition to this, environmental aspects such as the wind and tide will need to be overcome to complete the challenge, whilst also considering certain suitable corrosion-resistant materials inside our vessel. Other than this, the regulations we've had to comply with are the Maritime UK Industry Code of Practice, which we have taken from that we would need an all-round white light for visibility whilst we're at sea, and all of this is going to have to come within a £500 budget, provided we're given the hull already by the MAC Challenge team. I'll now hand you over to Andy to talk about the programming.
For the computing, we had a choice between a Raspberry Pi and an Arduino. The Raspberry Pi is what we chose because it has built-in Wi-Fi, which means it can communicate better with other devices. As well as this, it works better with Python, and the Arduino uses C. And our team, as a whole, has more experience with Python than Arduino. A Raspberry Pi can also do multiple threading at once. This means it can do multiple processes, so it can quicker and do more calculations at once, meaning it's better suited for data calculation. For data transfer, we had to choose between a 4G dongle, a mobile phone, or radio transmitter. We chose the 4G dongle because the mobile phone would take up too much of our data and the radio transmitter would not be able to communicate with other devices as well. For example, our website and anything else we used to communicate with the drone. And for location, we had to choose a GPS chip with a gyro compass and a mobile phone. The GPS chip with gyro compass would have everything we needed, be able to tell direction and where it is, and would not take as much as a budget as the mobile phone would. For movement, we created two flowcharts. The flowchart on the right defines the forward movement, where 0 being off, 1 being on, and 2 being backwards. So if you wanted the drone to move forward and to the left, you'd have the right motor on, left motor off. And the other way around for going right. And to go in reverse, both of them will be in reverse. This is very simplified as we would have a multi-speed system rather than just 2-speed. For the rotation, it's done by the left algorithm, which works by powering the motors individually. So when the left motor is in reverse and the right motor is forward, then the drone will rotate on the spot. This would all be calculated by the Raspberry Pi within the drone. Collision avoidance would be achieved using a series of ultrasonic sensors placed around the exterior of the hull, meaning that if there's any obstacles in the way of the drone, then it would detect the objects and move out the way of it. This works by having the ultrasonic sensor send out a signal which, when it hits an object, will bounce back and be picked up by the receiver. It would use the speed of sound and how long it took to reach the object to find a distance away from the object. Colour detection would be done by the Raspberry Pi. It would have a camera mounted on the phone which would take a snapshot. This photo would be analysed by a PiPhone program which would find the colour at the centre of the frame and use an algorithm to detect the colour and select it from a database. This would work well with contrasting colours, and it would have a select few colours in the algorithm which would be able to detect from. So this is so that if there is any colours which are similar to anything else around, it would be a better detection because it would already detect for those colours. I'll pass you back to Joe for navigation.
Yeah, so for navigation, we will have to plan our route before. We will begin by typing in the required GPS coordinates and to create checkpoints for the direction of travel into the user interface. So then the initial route is then planned. The current location is then compared with the destination, and this is something that will happen throughout the whole voyage that the vessel will be taken on. The distance to the next checkpoint can be calculated using the current location, and Pythagoras' theorem. The required bearing is then calculated and the new heading is obtained. The vessel will alter course if required while constantly analysing the bearing and distance to the checkpoint. The code will cease when the vessel is within a radius of the checkpoint. Visual sensors will be used to locate the buoy. So that is our essential basic navigation. We would use the code on the right hand side of the screen, and then this is all used together. And now I'm going to hand you back to Matthew Prowse, who is going to talk about our future projects and our current project 15.
Yeah, so thank you, Joe. So yeah, I just wanted to demonstrate a bit about what the students have been doing this year. So regardless of the Marine Autonomy Challenge, we were already working on, and we called it Project 15 because the students came up with it and they thought it was a good, and it is, well, I don't know what I'm saying here, but anyway. So yeah, so as I say, the students have basically designed a primarily like a catamaran, which ultimately is going to drive through the water and pick up litter as it goes along. So as you can see from the diagram, the way it's shaped is ultimately it basically scoops up litter as it goes through the water. So we used a program called MaxEarth, which we use for our sort of whole design. Then from that we can basically create shape using we've got an industrial laser cutter which we basically then use to make a former, which then we were going to make a plug to basically make the hole. So this is already in production at the moment. So this is pretty much the stage we got to before we went into lockdown. So again, next year all the students that you've just heard from will be coming into the second year. Ultimately, it's hoped that we can progress the Marine Autonomy Challenge, or if not, we will be progressing Project 15 as it is. So, we're really passionate as a group and as a team that, automation is the future of, cleaning up the oceans. Okay. Again, one of the reasons why we're very passionate about this is that we are in what we call a local seaside town. And you only have to walk around the local area to see that this is a problem and a global problem as well. So hopefully when we get back in September, we intend to do some testing to get the vessel on the water and start building the algorithms and the programs. So thank you very much for listening. Thank you to the students as well, and hopefully we'll see you all next year.